So say we want to tell the difference between the R and the S enantiomer of a molecule. So the R and the S enantiomer of the molecule. Well, before we can do that, we need to understand what it means to have a chiral center or a stereogenic center. And so if we start with a carbon atom, because this is organic chemistry after all, and organic chemistry is based on carbon, and we all know that carbon can make 4 bonds. So we'll draw 4 bonds here. And basically what it means to be a stereogenic center is to have each one of these bonds attached to a different molecule or a different ligand. So if this was a stereogenic center, then perhaps we would have a hydrogen there, maybe a nitrogen here, and here maybe another carbon, and here maybe like a fluorine. So as you can see here, each attachment is a different molecule. So this would count as a stereogenic center. This is a stereogenic center. And if we were to determine the configuration of this, whether or not it's R or S, it's basically just a matter of assigning priority to each atom attached to it based on atomic number. So we know that fluorine has the highest atomic number, so we'll give fluorine a 1 because of first priority. We know that nitrogen has the next highest atomic number, so we'll give that a 2. And carbon has the 3rd highest atomic number, and hydrogen is the first element on the periodic table, so that's obviously the last. And so we've assigned priority, so the next thing to do is to orient it in a way that allows us to basically count, determine the configuration. And so the rule for this is there's just one rule. It's that you orient the atom with the lowest priority, so in this case it'd be hydrogen, to be in the back. So as we can see right now that fluorine is in the back right now, we would reorient it so that hydrogen is in the back. And so we'll just go ahead and do that right here. And so we would, let's see, if we twist it this way, then hydrogen would go back here, and then fluorine would go up here, and let's see, nitrogen would go here. And we're basically just flipping it this way. We're kind of like doing a 180 right here, and so nitrogen go there, and so carbon would flip over and then go there. Okay, so we've flipped it over. We have our lowest priority atom in the back, and we'll just put these numbers back here. Okay, so we have it oriented correctly. We have the numbers assigned, and so basically we just count from 1 to 3. So 1, 2, 3. And if we draw an arrow, we kind of go 1 to 2, then from 2 to 3. And we can tell right here that the arrow we've drawn, or like the kind of like the circle that we've drawn here, goes counterclockwise. And so we've gone counterclockwise here, and counterclockwise. And so with being counterclockwise, we've gone basically left. And so we would identify this as an S enantiomer, because S refers to left, and actually S in Latin refers to sinister, which basically means left, and R in Latin refers to rectus, which basically means right. And the easy way to remember that is rectus and right both start with R, and so the one that doesn't start with R is obviously the other one, it's left. So here we have an S enantiomer because we're counting to the left, we're counting clockwise, and so we know it's S. And so if we were to, let's reproduce it down here. I'm just drawing the same molecule down here. And so if we take the enantiomer, which as you all know is the mirror image because This is a chiral molecule, and chiral is just the same as handedness. Your two hands are not superimposable on each other. They do not superimpose perfectly. And so if we take the mirror, your hands are mirror images, and so this is also a mirror image. If we take the mirror image here, and if this is the S enantiomer, then this has got to be the R enantiomer. And we can verify that here by checking our work. And so if we assign priority again, like we did before, 1 goes to 2, we draw our arrows, 2 goes to 3, and then 3 goes back to 1. We can tell that this one curves to the right, and so it's clockwise. It's clockwise, which means it goes to the right, which means it's R. So that's basically how you do it. And so you might be wondering, what does it matter if, one's an S enantiomer, one's an R? They both have the same attachments to it. They both look the same, basically, never mind the mirror image non-superimposability. What's the big deal? And I can show you with an example of ibuprofen. Now, as we all know, ibuprofen is a wonderful anti-inflammatory drug with analgesic properties, and in the case of ibuprofen, it actually makes quite a difference which enantiomer you have. And so if we take a look here at the two enantiomers of ibuprofen, you see this one's the R. We have the methyl group right here. We have the sp2 hybridized carbon right here, and we have the carbon attached to the oxygen right here. And over here, we can see that it's clearly inverted. The stereoisomer here is inverted, and so here's the R enantiomer, here's the S enantiomer. And as it turns out, only the S enantiomer has these anti-inflammatory and analgesic properties. And so when you're taking ibuprofen and you're getting the benefits from the therapeutic effects of ibuprofen, you're actually only getting the benefits from S-ibuprofen. R-ibuprofen actually is non-therapeutic. And so if you're wondering, when you go out to the supermarket and buy a bottle of Motrin or Advil or, in other case, ibuprofen, brand names for ibuprofen, you're actually getting racemic mixtures of ibuprofen. And that just means that you're getting basically half of S and half of R. And this is actually pretty common for pharmaceutical companies to sell racemic mixtures because racemic mixtures are actually very difficult to purify and separate. It's actually quite difficult to separate R-ibuprofen from S-ibuprofen because even though they're stereogenically different, they have a lot of the same physical properties, and so it's not possible to separate them using traditional separatory methods.